Okay, this lecture is over chapter 12 of your textbook, which is on recursion. So in this chapter, we're going to learn what recursion is. We're going to talk about how you go about solving problems with recursion. And then we're going to see a number of examples of algorithms or problems that lend themselves to being solved with recursion very well. So recursion is when you have a function that calls itself, which will call itself, which will call itself. That's what recursion is. You can have a way, or you need to have a way that typically involves some type of decision, maybe an if or an if-else statement, that defines when the recursion should continue. Because if the function just calls itself, you've basically created an infinite loop or infinite recursion, and your program is never going to end. Another thing we talk about is the depth of recursion, which is how many times a function is going to call itself. So here we have a picture. We're in our main program and it calls the function, and it is going to, it looks like, go through until the value of times is 0. So it goes in, it calls itself, the values of time is 4, it calls itself values of time is 3, etc. until the sixth call of the function is called and values of time is 0. So the function is ultimately called 6 times. The depth of recursion is defined as how many times a function calls itself. So the first call was made by the main program. So in this case, the depth of the recursion is 5. How many times did the function call itself? Here is some code that we might have had. It defines messages, and if messages is greater than 0, we're going to print this as a recursive function, and then we're going to decrement times by 1 and then call my function myself again. So that's how you create recursion. You have a function message that within the body of the function definition calls itself. So that's what they're showing you there in this graphic. There are some problems that lend themselves very well to recursion. There are other problems that may not. A lot of these programs could be solved by loops, but sometimes the logic of solving them works much better with recursion. Now, kind of the penalty you have is you're calling the function over and over again, and each of those function calls has some overhead associated with it. Setting up new variables, new local variables, that type of thing every time it's called, plus transferring control to and from the function over and over. So, like I said, some things are just easier to solve with recursion. Now, we have something called the base case, which is if the problem can be solved without recursion, you just simply solve and return it. So that's kind of the last call or last recursive call of the function, if you will. And then all other cases will keep calling the recursive function over and over again until they get to that base case. So that base case would be where you simply return an answer or a value without recursing any further. So the kind of classic first example of recursion is calculating the factorial of a number. So the factorial notation is written as a numeric value with an exclamation point after it. And basically what it means is you take that number, so if that number is 5, you multiply it by successively subtracting 1 until you get to the value 1. So it'd be 5 times 4 times 3 times 2 times 1. So the given fact is, or a fact is, if n equals 0, 0 factorial is 1. So if n is greater than n, then n factorial is, like I said, 1 times 2 times all the way up to the number itself. Now in this case, n equals 0 is our base case, because we're just simply going to say if n is 0, the answer is 1. And then our recursive cases are going to be anything that is greater than 0. And if you look at what I told you, 5 factorial is 5 times 4 factorial. So you can just simply repeatedly call the function over and over, subtracting 1 each time and passing that in as the argument until you get to the base case, which is n equals 0. And then it kind of recurses back and multiplies the answer by the value that was passed in as the argument, gets a new answer, passes that back to the previous call, which is that answer times whatever value was passed into that call of the function. So here is our definition of the factorial function. It's very simple. If we pass in 0, that is, if num equals 0, simply return 1. Otherwise, return the number that was the argument times the factorial of that number minus 1. So this is showing you how it goes through and calls. So basically, I don't think they showed this really well, because you have to look at the middle line of each of these and then kind of look at the bottom line coming back. So we call the function for 4 factorial, so the value of 4 comes in. So we then call that function with a value of 3, we then call it with a value of 2, we then call it with a value of 1, and then finally we call it with a value or an argument of 0. The return value in that case is 1. It goes back and calculates back, so 1 times 2 times 3 times 4. So when the very first call to the function returns at the very top, as we're coming back up through this call or recursion list, is 24. So that is an example of calling that function for 4 factorial. So basically, each call to a recursive function reduces the problem until we get to a point that the recursion will stop. Typically what happens, not always, but typically, we have an argument that is decreasing or increasing in value until we get to a certain value. Now then, what we've been talking about up to this point is direct recursion. That is, a function named x is calling itself a function named x, which is calling itself a function named x, etc. Indirect recursion is when we have a function a that calls b, but b calls a, which calls b, which calls a. So we have 2 or more functions that are ultimately recursing amongst themselves. So that's direct and indirect recursion. So what they're doing is they're giving some examples of recursive algorithms. One of them is adding up a list and an elements. Now here's one where if you want to sum a range of elements, you would just go through and do a for loop for each element in the list, add it to an accumulating sum. So this is one of those examples that they're showing you, yes, this can be served or this can be solved with recursion, but it is not necessarily the best way to do that. So our best case is if we're at the end of the list, then we're done, return 0, because adding 0 to any value is going to give you that value back. Our recursive is to call the current number, or take the current number and then sum all the elements after it in the list. So we will go through and add each of those in a recursive call to the algorithm. So here, if we're past the end of the array, return 0. Otherwise, return our current value we're looking at plus the sum of all the following values in the list. So, like I said, here's an example. Yes, we can solve this recursion. It makes a good example because it's easy to understand. However, in real life, this is probably not the way you would solve this problem. The next is a Fibonacci series. Fibonacci series actually has 2 base cases. These are cases where you just kind of give an answer, because Fibonacci series of 0 is 0 and a Fibonacci series of 1 is 1. And then the way we calculate a Fibonacci series is if n is greater than 1, then the Fibonacci value of that number is the Fibonacci series or answer of the number before and the number before that. So it's basically looking at the 2 values before that and adding them together. So there is the definition. We have our 2 base cases with an if, else if, and then finally the last if, or the last else, is take the Fibonacci sequence or series answer for the 2 numbers before and add them together. So that is a good recursive function to solve. Another one that I don't recall seeing, and I think this is a great example though, is finding the greatest common denominator. So basically you have 2 values and maybe you're going to add or subtract them. So you have to have a common divisor, that is a common number under the line within a fraction. So basically, if x can be evenly divided by y, then the greatest common denominator of x and y is y. Otherwise, we want to call that with y and the remainder of x divided by y. As far as, I'm surprised they didn't put the 2 slashes here because it's really the percent. So it's the mod operator, which does give us the remainder of x divided by y. So here's the function. If x is evenly divisible by y, that is the remainder is 0, then return yes. Otherwise, call the GCD function again with x and x mod y to try to solve the problem. Another classic example, which I've seen many times in recursion, is the tires of Hanoi. And basically what happens is you have a base that has 3 pegs, and when you start out, all of the pieces are on 1 peg in decreasing size. And the goal of the game is to remove really from one peg to another peg. Here they're saying move it from the left peg where you start over to the right peg. And you do this by rearranging the disc. And the exception is that a disc cannot be placed on top of a smaller disc. And then the last one is kind of cheating, or to prevent cheating. You can't take one of them off, set it to the side, and then work on solving the problem and then bringing it back in. So you can move one disc at a time, and all the discs have to stay on the pegs. So here's a picture. This was actually one of my favorite things to build in woodworking shop class in high school. I have a bunch of these. I like the problem, and it's real simple to build. So I made several of these. Here they're showing you with 3 discs. I think mine had 5, 6, or 7 on it when I used to build these. So this is what the tires of Hanoi look like. So here they're showing you basically move the small disc to the right, move the middle disc to the middle, put the little disc on top of it, move the big disc to the right, move the little disc to the left, take the middle disc, put it on top of the big disc, and then take the little disc and put it on top of the stack. And now you have moved the 3 rings or the tire from the left peg to the right peg. So, with 3 discs, it's fairly straightforward. Still takes you 7 steps to get through. So as you add an additional disc on the bottom, the number of moves you make goes up pretty quickly. So basically your problem is move end disc from peg 1 to peg 3 using peg 2 as a temporary peg. So the base case, n equals 1, is you're going to move a disc from peg 1 to peg 3. Otherwise, you need to move n minus 1 disc from peg 1 to peg 2 using peg 3 as the temporary, and then remove the remaining disc from 1 to 3, then move all the ones that are on peg 2 to peg 3 using peg 1 as the temporary peg. So that's kind of hard to say, but here's what the function looks like. So we call the number of discs that we're moving, the from peg, the to peg, and the temporary peg. And then if the number is greater than 0, we're going to print out what we're moving, and then we're going to call the move disc function. So we're going to do the recursion. Like I said earlier, there sometimes are reasons to use recursion, and sometimes it's best not to use recursion. Like I said, one reason or one thing you have to think about is calling recursion. In the case of summing up the elements of the list, you would definitely not want to use recursion. It's not worthwhile. But for something like Tires of Hanoi, especially, recursion is good. Even for Fibonacci series, it is good. The factorial one, interesting example, but probably more efficient and just as easy to understand if we did that with a loop. You just need to take that into consideration versus how much easier does it make to solve the problem and write the code. So that finishes up the chapter on recursion, and here's a list of some of the things that we covered in this chapter.